Good morning, everyone. I am João Antônio Martins from University of São Paulo, Brazil. And this is our third lecture of our 2020 IEEE Electric Device Society South Brazil chapter webinar on micro and nano device. This chapter is the chapter chair. I am the chapter chair, and Professor Paula Agopian is the chapter vice chair. Okay. We start that webinar last week when we had two presentations, two lectures, Professor Korklais on October 13 and Professor Durga on October 15. It was fine, many people, a lot of questions. I think it's a good way for us to have opportunity to talk with that very important people from outside. And this week, we will have another excellent presentation from Professor Adelmo Ortiz Conde from Universidad Simón Bolívar, Venezuela, with the title Electrical Characterization from Micro to Nano Era. Will be today in some more minutes. And next week is already organized another presentation from Dr. Bertrand Pervet from IMEC Belgium with the title Advanced Transistors for High Frequency Applications next Thursday at same time, 11 a.m. You already know, you can always, all the time, make a free registration in order to receive a participation certificate. And all presentations, you have to go to our channel with that link, and all presentations start with this YouTube channel. Well, today we have a pleasure to have with us Professor Adelmo Ortiz Conde, and he has opportunity to come here to Brazil many times. We have a lot of interesting, good joint work. And I asked to Professor Adelmo to give us this time a webinar, once it's not possible to go from Venezuela to Brazil, but I hope next year we have opportunity to get Professor Adelmo again with us. The presentation will be around 50 minutes, plus or more some minutes, and more 10 minutes of question and answer. Professor Adelmo Ortiz Conde received the Professional Electronic Engineer degree from Universidad Simón Bolívar, USB, Caracas, Venezuela in 1979, and a Master and PhD degree from University of Florida in 1982 and 1985. He has co-authored one textbook, a very interesting textbook, called Analysis and Design of MOSFET, Modeling, Simulation, Parameter Extraction, and over 106 international technical journal and conference articles, including 90 invited review articles. His present research interests include the modeling and the parameter extraction of the semiconductor device. Dr. Ortiz Conde is an Electric Device Society Distinguished Lecturer and Chair of IEEE CAS and ED Venezuelan chapter. He was editor of a very famous periodics of our area of IEEE Electron Device Letter in the area of silicon device and technology from 2009 and 2018. He was the Regional 9 editor of IEEE EDS newsletter from 2000 to 2005. He is a member of editorial advisor board of various technical journals, microelectronics, reliability, and many others. I'd like to welcome Professor Adelmo Ortiz Conde, and thank you very much for accepting to give us a presentation. Professor, please. Thank you.
Thank you very much for inviting me to this talk. And The outline will be two topics. The first one will be diode and solar cell. In this area of diode and solar cell, here we have the most important papers about modeling and parameter extraction. In 1949, it was the first single exponential model with n equal 1 and the series resistance. This model was developed by Julius Shockley. In 1957, the first paper, the first article in which they present a method to extract the single exponential model without series resistance. In 1963, we find the double exponential with series resistance and parallel conductance, GP. And then in 1979, we have a method presented by Norder. This was a very interesting and very clever method in parameter extraction. 1982, the first integration method for solar cell. This was developed by a group in Spain. 1984, it was presented the first paper in which they present analytical method using viewpoint to extract the parameters. These are approximated methods. In 1987, we find the lateral optimization method using the voltage equation. So instead of minimizing the error of current, it was a lot easier to minimize the error in voltage. In 1993, we have the integration method to extract N and RS for diode. In 1995, the integral difference function and the G method. 1999, function A and B. Year 2000, analytical solution for a diode with RS and GP. It is very interesting that the Lambert function, which is used for the analytical solution, it was used in electrical engineering in year 2000. But this function, it is a very well-known function used in many engineering areas, and the electrical engineering, we didn't know it. Year 2004, the analytical solution for solar cell with series resistance. 2006, vertical optimization method using current equation. The same year, the co-content function method. Year 2007, regional optimization. Year 2010, lateral optimization for double exponential model. Year 2012, vertical optimization of solar cell with RS and GP. The same year, alternative multi-exponential model for solar cell. Year 2013, Sandia sequential approach. The same year, approximate lateral optimization. Year 2018, the delta G method. And this year, an algorithm for maximum power point calculation of solar cell, which is published in November of this year. The outline for MOSFET is, the first paper is in 1964, and the title of the paper is Theory of a Surface FET. If you look at this title, you will think, well, this has nothing to do with MOSFET. Well, the surface FET, that was the first name that it was given for MOSFET. At that time, the publication was called Surface FET and not MOSFET. And in this article from 1964, it is the first quadratic model. In 1968, we find a modeling of insulated gate FET, and now they call it insulated gate FET. This is actually a MOSFET. And in this article, it is presented what is nowadays known as SPICE level 1. 1986, they realized that the mobility degradation and the series resistance have the similar effect in the transfer characteristic. 1979, 1980, they realized that in order to separate the effect of the mobility and the series resistance, they need to use various mass channel lengths. And this method was presented by Terada Muta in one article, and another separate and different article by Cher. 1987, the second derivative method is presented. 1988, the Y function is presented by Gibaudo and Jain. Again, these are two separate articles. Gibaudo is doing an article and Jain is doing a separate article, and they present the same idea but with a different application. 1994, 1996, the extraction of the asymmetric resistance in a 4-terminal MOSFET. Year 2001, the method based on the function H for non-crystalline MOSFET is presented. Year 2010, the transconductance to current ratio method is presented. Year 2015, The gate-all-around MOSFET inspired the nanowire device. The same year, the FinFET and the nanowire inspired the nanochip device. This is the device that looks like it's going to be the future device or the present device. Year 2050, the back-enhanced SOI MOSFET. This is a very interesting device because the device is very simple to fabricate, and it was designed and fabricated in Brazil. Year 2016, a method based on constant ID is developed in which you plot the drain voltage as a function of gate voltage, and from this plot you extract the parameter. Year 2020, the asymmetric resistance in 3-terminal MOSFET is developed. Well, you may ask, well, what is the difference between 3-terminal MOSFET and 4-terminal MOSFET? In the 3-terminal MOSFET, you don't have the body contact. This is like, for example, the thin film transistor. They don't have body contact, and you need a special method to extract the parameter. Here is an interesting plot that gives us an idea of the development of the devices. So the electronics actually start in vacuum tube here, 1906, with Lee Forest. Then it's very interesting to mention that the idea of the MOSFET is from 1926, and it was presented by Lilienfeld. Then the idea of the MOSFET, it was also presented by Lilienfeld in a patent in 1928, but of course they did not fabricate the MOSFET. The idea of the inversion MOSFET in 1935. The fabrication of a PN diode is from 1940. And then the fabrication of the first transistor is 1947. And the idea of the bipolar is 6 months later, 1948. Then the hybrid integrated circuit, the planar integrated circuit, the CMOS circuit from 1963, Moore's law from 1965, the first microprocessor 1971, Zener scaling rule 1974. These rules were valid up to about year 2000, when they are not valid anymore. And then we have a strain silicon, year 2002, high-K metal gate, year 2007. The FinFET, it is used by Intel in year 2012. Here we have Russell, 1940. Russell from Bell Lab fabricated the first PN junction diode and also a solar cell. It is interesting that they fabricated that, but at that time they didn't realize what they were doing, and they didn't publish this. In a recent publication in IEEE Spectrum, Riordan published the notebook of Russell, in which he was doing that, and he did that, but he didn't publish it. Actually, the first publication of solar cell is from 1954, and in this work in 1940, he realized about the diode and he realized about the solar cell, but he didn't understand very well what he was doing, I guess. 1947, the first transistor is done by Bardeen and Brattain. This is the contact transistor. It was done by Bardeen and Brattain, and then Brattain wrote many years later, Bardeen and I were simply trying to make a good field effect device, and as a result, we were put in a position to observe for the first time a phenomenon now called the transistor effect. His boss was William Shockley, and Shockley 6 months later, he developed the idea of the bipolar transistor, because when Bardeen and Brattain did that, they didn't understand that they have an NPN, and in fact, the point contact transistor was fabricated for a very short period of time. Then the idea of the bipolar NPN, made by Shockley, it was a very big advance, and Bardeen, Brattain, and Shockley received the Nobel Prize in 1956 for the development of the transistor. Shockley wrote the following: what I say about myself, and I am sure most creative people will say the same thing, is that when we look at how long it took us to get certain ideas, we are impressed with how dumb we were, on how long it took us, and how stupid we were. But we have learned to live with this stupidity, and to find from it what relationship we should have seen in the first place. So this is I like very much this writing, because You know, when you are trying to solve a problem and you cannot solve the problem, well, if Shockley used to think this about himself, well, so we are. It's not so bad that we are not so intelligent. Okay, the first single exponential model for a p-n junction with n equal to 1 and Rs was developed also by William Shockley in 1949. This is a copy of his paper here, and we see a picture that he presented in that paper, and we recognize here the quasi-equilibrium approximation, you know, the idea that the quasi-Fermi levels are flat, and this is fundamental in order to get this equation. In year 1949, in the same paper, he realized about the effect of the series resistance, and he have an equation in which here they have the resistance. So this is the equation. In 1957, we find the first paper in which they extract the parameter in an organized way. So then the idea of, you know, plotting, first you have the current is given by this, then you neglect the -1, and then by neglecting the -1, you can take the log in both sides, and you get this. And then if you plot the logarithmic of the current, here is the plot of the logarithmic of the current. Here in blue, this side is logarithmic scale. Here in this side is linear scale. So if you see the diode in a linear scale, it will be like this. If you see the diode in a logarithmic scale, it will be this one. So if you see the data, you get a straight line. And if you extrapolate the straight line, the slope yield to MBTH, and the intercept yield to I0, the intercept here. Of course, if you get very close to 0, the -1 is important, and the point deviate from the straight line. But this paper was presented by Sa, Noyce, and Shockley in 57. I guess many of the people that is listening this talk, they were not born at that time, 57. And in 1963, single and double exponential with series and shunt resistance is used in modeling. So here, for example, we have the model that they were using. Here they are presenting the short circuit current as a function of the irradiance. And here they have the equation in which they present series resistance, and they present double exponential diode. And here we have the vertical optimization method. This is the most simple idea. If you want to extract parameter Rs and the parameter of the diode, you feed this equation to the measured data. Of course, the problem that you have here is the current is here and the current is here. So this is an implicit solution. You need to do an implicit solution in order to calculate the error in current, and this is not computationally efficient. 1979, the method by North. This method contained clever mathematical ideas, and it was developed for Schottky diode with n equal 1. The following notation is adapted to p-n junction. And here is the model that they are using. It is very interesting if you plot the citations of this paper. The paper is here, published in 1979 in Journal of Applied Physics. The citation is going like this. So here you have the number of citations, and here the years. So it's very interesting to see that the first 10 years, the paper has very few citations. And then 30 years later, it has a lot of citations. Now it has 978 citations. So this is very interesting when you publish a paper. If you get very few citations at the very beginning, well, don't get upset about it. Maybe later you will get a lot of citations. You have to be optimistic. So this is a 41-year-old paper, and it's still very popular, and the people is using it. Let's talk about the method by North. He starts with this equation. He knows that the voltage can be expressed like this. And then he said, well, let's define a new function. We will call this function North function here. This is the function that North proposed. B divided by 2 minus BTH log of I divided by IX, where IX is an arbitrary value of current. This function presents the minimum value which is independent of the selected value of Ix. And this is proof here. So if you take the derivative of the north function, you get this. And using the VDI is equal to this, from equation 2, you substitute 5 into 4, and you get this. And doing the mathematics, you get that the derivative is 0. If this is 0, this implies that R is equal to VTH divided by I mean. And you see that the I mean depends only on RS and VTH, and it doesn't depend on IX. So then, after you get I mean, you evaluate I0 from the equation number 1, and this is here. And where B mean is the value of the voltage at the minimum of the function of north. So the disadvantage of this method are the ideality factor is assumed to be unity, and the extracted parameters are based on few data points near the minimum of north function. We can say that this is a clever transitional method which extracts the parameter at the value where the resistance and the diode are important. And here we have, for example, extraction using measured data. The measured data that we presented previously, we are now using it. And the idea is the previous data has an n of equal 1 or 5, and these are the parameters that we were extracted. And now, since n is equal to 1 or 5, and the method is only valid for n equal 1, well, we adjusted the thermal voltage like this, and now we apply the north method using this thermal voltage, and we have different IX, and we see that the minimum is independent of IX. IX is 10 to the minus 11, 10 to the minus 10, 10 to the minus 9 for the tricolor. We see that the minimum is independent of IX, and with these two values of the minimum, we extract the parameter RS40 and I0 756 picoamp. Well, this is it's not exactly the same that we extracted before, but they are close. And here is we do the playback and the measure data to see how different are to see how is the result, and and the simulation using the parameter extracted with North method agree very well with experimental data for values close to P mean, which is about 0.4 volt. Here we see very good agreement, and here there are some differences, and here there are some differences. The limitation of n equal 1 has been removed by various authors, and here are the papers. Now let's talk about the first integration method. The first integration method for solar cell was in 1982. It was done by Araujo and Sanchez from Spain. This is the paper. The idea is to start with the equation of voltage, which is this. You assume that the current is a lot greater than I0, and also that IPH, the generated current, is a lot greater than I0. You solve the integration of B with respect to I, because this can be integrated, is this one. And you do the approximation, and then you changing the variable RS. Changing variable RS is evaluated from this equation. You evaluate RS, and RS is equal to this. You use this approximation, and then the idea is by using the integration of P with respect to I, you get RS. In 1984, we have a very interesting article. This is a very interesting and practical article. The idea is to get approximate analytical solution using few points. Using few points is, the point that you get from the data sheet. Let's say that you know the open circuit voltage, the short circuit current, the voltage and the current for maximum power, which is Vmax and Imax. So then the idea is using this point, you want to extract the parameter. Of course, you are going to do approximation. For example, you define GP0 or the inverse of RH0, the derivative of the current with respect to the voltage in short circuit. You define RS0 as the derivative of the voltage with respect to the current in open circuit. You do this approximation, and then the solution are this one. So then the idea is you can extract N, IPH, and I0 in an approximated way. And this was done by Fang and by a group of China in 1984. It is interesting that in year 2009, Batselis, in a review article, review 17 approximate analytical methods using viewpoint. Here is the list of the 17 articles. It is interesting that this year, 2 more approximate analytical methods were presented. And here are the papers. So this is, I guess, for the people who is working with solar panel, it is very important to have a very fast approximated method. 1987, lateral optimization method using the lateral equation. The idea is use this equation and do the fitting with measuring the error in voltage. So instead of measuring the error in current like vertical, you do the error in voltage, which is lateral. So this is equation. It's very simple. It's not it's an analytical solution. You don't need any iteration. So this is computationally efficient, and it requires using a simple log function. 1993, the first integration method to extract N and RS for diode. The idea is you have this model, you integrate IDB, but integrating by part is B times I minus B, the integration of B with respect to I. So B is given like this, you substitute B here, and you obtain this. And now you assume I is a lot greater than I0, you get this result. And the idea is you measure the current, you evaluate the integration of the current with respect to the voltage, and then the integration of the current with respect to the voltage, you do a quadratic fitting. By doing a quadratic fitting, you obtain RS and N. This is a much simple problem of fitting an explicit algebraic quadratic equation. In 1997, Kaminsky improved the previous method by realizing that you can integrate from an arbitrary point BI, II. If you do this, this is not 0 anymore, this is BI, and the result is this one. And this equation is valid for a current a lot greater than I0. In 1995, here is an interesting idea, the integral difference function and the G method. So we start by using a concept presented by Chua in 1973, this article. Chua, who is a person who has done a lot of work in circuit theory, defined the content and the co-content. The co-content is if you plot the current as a function of the voltage, the co-content is the integration of the current with respect to the voltage. This is the co-content. If you integrate the voltage with respect to the current, this is called the content. So this is the notation of Chua. And now, if we have a straight line, let's say that I, as a function of B, is a straight line, is linear. The content and the co-content are the same because these two areas are the same. So if the current is linear, content and the co-content are the same. Therefore, if you define an operator D, content minus a co-content, the operator D will be 0 if you have a straight line. On the other hand, if you don't have a straight line, the two areas are different, and content and co-content are different when the function is non-linear, and therefore D will be different to 0. In 1995, the idea is using D, we apply D to a diode, for example. If you apply D to a diode, the effect of the series resistance is eliminated. So you get only the function D of the diode. Substituting the Shockley equation in the function of the diode, you integrate this and you get the following. Function D is this. And then if you divide D, the function D, by the current, you get function G. And you get rid of this I, and you get MVTH log of I minus log of I minus plus 2. So then the idea is you plot function G as a function of log of I, and you should get a straight line, and from the intersect, you get I0, and from the slope, you get MVTH from the slope. Here is some experimental data, the same diode that we have been using before, and we have here a plot of G as a function of I, we see a straight line, and we get this parameter. So they are very close to previously obtained by lateral optimization. 1999, function A and B for diode. the series resistance is negligible at very low voltage. So you can model the diode like this. If a diode needs to be modeled with two diodes, you can model like this because the series resistance is negligible. But the problem is, if you are working at very low voltage, you cannot neglect -1. If you neglect -1 at very low voltage, it will be a mistake. So then in 1999, these two functions were proposed. Function A, which is the co-content divided by I, that means the integration of the current with respect to the voltage divided by I is function A. If you do the mathematics, you get that this is equal to MVTH minus I0, which multiply B divided by I. So then the idea is, you measure the current, you evaluate this, you plot function A, which is coming from the measured data, and function A plot as a function of B divided by I, which you know these two values, should be a straight line. The slope will define I0 and the intercept MVTH. On the other hand, you can also do function B, which is the co-content divided by the voltage. If you do the mathematics, function B will be MVTH times I divided by B minus I0. So that means if you plot B as a function of I divided by B, the slope will be MVTH and the intercept will be I0. It is interesting to mention that function E has also been used in MOSFET parameter extraction, and it is known as function H. 1999, function A and B. They are applied here to a measured bipolar transistor, and we see that the functions are a straight line as should be expected, and the parameters are extracted. Year 2000, analytical solution for a single exponential diode with RS and GP. It is interesting. Here we have the equation for a diode and a series resistance only. Is this one. It is interesting that up to year 2000, everybody was saying that there was not an analytical solution for this equation. And you know, very good books like Graham Meyer and any good books will tell you that in order to obtain I, you need to solve this iteratively, numerically. It is interesting that in the year 2000, Banwell and Yakumar presented this paper in which they realized that the solution of this was this. And here is the W function. The W function is the Lambert function. And this is an analytical solution. And the Lambert function is a little bit like, has some similarity with the logarithmic function. The same year, this work was generalized having parallel resistance, and it was published the same year. Year 2004, analytical solution for a single exponential solar cell with series resistance. This paper was published by Jain and Kapoor from India, and they realized, using the Lambert function, that this problem also has a solution. And the idea is the implicit equation is here. The lateral solution, that was known, but the vertical solution, it was published by Jain and Kapoor, is this one. It is interesting that the year 2000, when we knew that, and we considered that was a very stupid, very simple to do. And in year 2000, we knew that solution, and we didn't publish it because we considered it was very simple to do it. And we were wrong. Jain and Kapoor published in year 2004, and they have received a lot of citations. And because this paper, the idea was very simple. It was to use the Lambert function that was used for diode, but it was very useful. Year 2006, vertical optimization method using the vertical equation. This was done by a group in Poland, and the idea is you have this problem. You know that the current is given by the Lambert function, so you can use this equation in order to minimize the error in current. It is interesting, this article, but I would think it's not very practical because, I mean, if you have this problem, the voltage is a very simple equation which only requires a logarithmic, so lateral optimization is a lot better. Year 2006, this is an interesting method. The idea is for a solar cell model like this, you can integrate the co-content. The co-content will be defined like this. We put here the short circuit current to make this 0 for B equals 0. You have that the current is given like this and the voltage is given like this. This is a previous solution. So then the idea is we will perform the integration, and doing some algebraic manipulation, we will obtain the function co-content in the form of a convenient purely algebraic expression like this. So then the idea is you have this. You put I here. You integrate this. You will get a lot of Lambert term, a lot of term with Lambert. And the idea is you recognize that the Lambert term can be rewritten as current or voltage. And after doing this, you will finally get this. Of course, this is something that you will not get in 20 minutes. Probably you will spend one day by obtaining this equation. But the useful of this equation, the beauty of this equation is you measure the current, you can calculate numerically this. When you calculate numerically this, you come here and you do a two-dimensional fitting. You will do a fitting with voltage and current. But the fitting here is a quadratic equation in voltage, and it is also a quadratic equation in current. So it is a very simple and efficient fitting. And by doing the fitting, you will extract CBI, CI1, and all these C coefficients. The C coefficients are related to a parameter of the circuit, like this. And the fifth coefficient is dependent of the previous four. And of course, if you know the coefficient, now you want to extract the parameter, RS, I0, and so on. And these are given by this. These are the solution. So you get GP like this, RS like this, N like this, IPS like this, and I0 you will obtain from the implicit equation. Year 2007, the regional optimization. The idea is you have the problem, and then you have this implicit equation. So both CD propose two different fittings for low and high voltage. The idea is for low voltage, the linear part dominates, and the implicit equation is approximated by this. For high voltage, the exponential part dominates, and the implicit equation is approximated by neglecting the linear term in B. So you get this. So then the idea is doing two fitting, you extract the parameter. Lateral optimization for the double exponential diode model. If this is if you have a two diode model like this one, but in this one n equal to 1 and this one n equal to 2, this is the problem that you have. So for this case, there is a solution. If this n2 is different to 2, the solution is not valid. The solution was presented in collaboration. It was presented by us in collaboration with Pavanello from Brazil and Flandre from Europe. A generalization of the lateral optimization for the double exponential diode model was recently proposed by Degas and De in year 2007. He realized that if this is equal to, if this n is equal to n1 and the other n is equal to 2n1, this is your problem. There is a solution, and a global fitting procedure can be used. A vertical optimization for solar cell with RS and GP, that was done by a group in Spain, Pozo, Romero, and Arredondo. The idea is they use this equation and they fit this equation. There is in year 2012 the alternative multi-exponential model for solar cell with resistance. The idea is, let's say that you have this circuit model here. Then you have here the linear part in blue, and here you have the non-linear part in red. So the linear part, you remember circuit theory, you can transform that in the Thevenin. So here is the Thevenin. So this is the Thevenin voltage, and this is the Thevenin resistor, and they are here. And then the idea is you say, well, this problem still is a problematic problem because the two diodes are, or the N diode, are difficult to calculate the current. So what you do is, well, what if instead of doing this, you do this problem? The resistor is put in each diode. So now you have several resistors. So this is an approximate solution of this. But what is the motivation of doing this approximate circuit? This approximate circuit is very interesting because it has an analytical solution. Given the voltage, I can calculate the current here because it's a diode with a resistor. And this current will be a summation of the other, so the analytical solution is given like this, where W0 is the principal branch of the Lambert function. And then in year 2013, the Hansen from Sandia do a modification of a previous method, and the idea is it's an improvement of the co-content function method. You start with this equation. The diode ideality factor N is obtained from the relationship between the open circuit voltage and the effective irradiance, and GP is obtained by using a modified approach of the co-content function, which will be described in the next view graph. I0 is estimated using the open circuit condition, like this, and IPH is determined as the short circuit. And then the modified approach to obtain the GP is the following. The co-content function is evaluated by first applying an spline interpolation method to measure data, and then using trapezoidal integration. As before, the following equation is fitted, and GP is evaluated from here. We consider that it is of paramount importance to use a sufficiently adequate integration algorithm, one that will produce negligible error, such as a closed Newton code formula with 7 points, as illustrated in the appendix in this article. We also recommend to use a small step voltage of 10 millivolts in the measurement. So we find interesting the Sandia sequential approach, but we criticize him for using trapezoidal, which is not as accurate and as a 7-point formula. In year 2013, approximate lateral optimization. The idea is you have this original equation for this circuit. Then the idea, there is an approximate solution for the voltage, which is this one. If you use this approximate solution, where you have here an M, and N is a joining factor, you can do an approximate solution. Year 2080, the delta G method is developed, and this is a variation of the G function. The idea is defining delta G as a function G minus G divided minus G evaluated at BR and IR. And if you do the mathematics, you get that this is equal to this, where BR and IR is a selected reference point. So then by doing this, the parameters are separate. N is equal to this, I0 is equal to this, and R is equal to this. So this method isolates the effect of each of the parameters. And here are the results. Here is the current as a function of voltage. Here are the G, and the N, I0, and R are presented here. A method by differentiation can also be analyzed. For example, if you start with this equation, you get dB, di is equal, the second derivative is this one, equal to this. You do more mathematics. So finally, you will get that N is equal to this, R is equal to this, and I0 is equal to this. So the mathematics looks fine. The only problem is, and this method isolates the effect of each of the parameters. The problem with this is, by using derivative, if you have measured data, the error will increase, and this will be a problem. And you have it here. Here you have simulations in red, measurement in black, measurement with the smoothing in blue. So we have the first derivative here. We have the second derivative. We have here, we start to see more noise, and then it has a lot of noise. So the method with the derivative is very good for simulation, but it's not very good with measurement. And finally, in year 2020, we have an algorithm for maximum power calculation. The idea is you have this problem. If you want to calculate the maximum power, there is not an analytical solution, but here you have a formula based in fixed point iteration. The idea is you get the value of IMP. You put in this equation. Function f is this long function which is here. With this, you calculate a new IMP. If this value is very close to this one, that means we are very close to a solution. So you do this iteration a couple of times, and in 5 iterations, you get the solution. Now let's talk about MOSFET. The idea of the MOSFET, year 1926, Lilienfeld. Then 1928, the idea of the depletion MOSFET. which is here. This is taken from the patent. It was essentially a non-doped depletion single bottom gate SY MOSFET. The idea of the inversion MOSFET, 1935, by Hill. Here is a drawing explaining the simplified idea of Lilienfeld. You have metal here, you have oxide here, you have semiconductor here. The semiconductor is very narrow here in this area. And the idea of Lilienfeld was the electric field deplete the carrier in this region, and in that way, I switch off or on. The classic MOSFET from the 1980s was like this one. This was the MOSFET that I used to study when I was a graduate student. In year 2012, this is the FinFET. The FinFET, this is a transmission electron microscope. It looks like this. And in a schematic way, it looks like this. The gates are right here, the oxide is here, and the silicon here. So the carrier are going through silicon, and the gate deplete this or enhance the conduction here. The Shockley unipolar JFET. This paper was presented in 1952. And the idea of this paper is that he modeled the conduction here. Here he have the gate here, and he modeled the conduction like a resistor controlled by the gate. And he started to obtain the quadratic equation. 1960, fabrication of the MOSFET by Kahng and Atalla. 1963, the CMOS circuit, it was developed by Wanlas and Sa. 1964, the theory of a surface field effect transistor, a quadratic model. It is here. It was done by Atalla and Moore. Moore law, 1965. The interest in Moore law has increased abruptly. We see this here, the excitation as a function of year. Moore, in year 2003, he was plotting here the feature size as a function of year, and the feature size is decreasing. It is interesting that the 8 virus is 0.1 micron, and that was year 2005, we were in that dimension, and this is the same size of what we are estimating to be the COVID-19 virus. 1968, the modeling of the insulated gate field effect transistor. This is a spice level number 1. This is a paper by Chipman and Hodges. And basically they obtained this equation, which is level MOSFET spice level 1. Year 1986, mobility degradation and series resistance has similar effect on the transfer function. So the idea is you have this equation, you have this model, and you have the effect of the series resistance on drain and source. You have this equation. So then, if you do, for example, we have here measurement in symbol, and the fit is the solid line. So if you do a fitting with theta equals 0, that means you are only assume R, you get very good fitting. Here is a logarithmic plot, and here is a linear scale. So this is the linear, this is the linear, and this is the logarithmic. So for a strong inversion, which is in this area, you get very good fitting, assuming theta equals 0. And the R that you obtain is 3 ohm. So this procedure yields an overestimated value of series resistance. So if you do the opposite, you assume R equals 0, and you do a fitting in order to get theta, you will get theta 3.3, and you get also very good result. So this fitting gives an overestimated value of theta. So what that means is from the transfer characteristics, you cannot extract both parameters because both parameters present very similar behavior. So the previous two fits remain as that it is not possible to simultaneously extract theta and R from the transfer characteristics, since both parameters present similar effect in this region. In fact, theta and R produce equivalent effect as a strong inversion and a small BDS. This was done in 1986, John did the following. If we have this equation, which assumes theta equals 0, and then he do this approximation, and he substitute the effect of the series resistance in the equation here. So he obtained this. And obtaining this, he realized that this equation, this Kr is like a theta. So this Kr is like a theta due to the series resistance. Therefore, theta R and R are equivalent in this model for this bias condition. In 1979, 1980, there was a paper by Terada and Muta and a paper by Cher, and they basically, what they do is they start with this equation. They assume that BES equals approximately to BES, so that means this voltage is approximately to this one. That means this voltage drop is negligible. And then they rewrite RFED like this, and then the final result is the measured resistance between here and here is R, which is the summation of these two, plus RFED, which is the resistance of the transistor. And the idea is if they plot Rm as a function of Lm, this will be a straight line. And from the straight line, they will extract R, and they will extract also the mobility degradation. And it is here, the plot of Rm as a function of Lm. And here, they two intersect all in one point, and this point, we amplify here, and we see that it's not exactly 1 point, but it's close to be 1 point. So the plot of Rm as a function of Lm is a straight line. The unique intersection of all straight lines for different BGS yield R and delta L effective. It is interesting to mention that the L effective, when I was a student in University of Florida in 1980, I was told that the L effective was closer than the metallurgical channel length. The metallurgical is the channel length from the junction to the junction. I used to believe that the L effective was shorter. It is interesting that we did a lot of simulation and we found that the L effective is larger than the metallurgical channel length, and the reason is because the effective channel region is where the gate controls the carrier concentration. And in this region, the gate is controlling the carrier because this region is very low dope, because it's very close to the junction. 1987, the second derivative method. The second derivative method basically is, let's say that you assume a spice level 1. So this is the current as a function of Vg. If you take the first derivative, you get a step function, because this is to a straight line. If you get the second derivative of a step function, it's a delta Dirac function. So that means if we go now to the real to measurement, if you plot the second derivative, the maximum of the second derivative should be very close to Vt. The paper was presented by Dawon in 1987. In 1988, Guibaudo and Jain presented two interesting papers. Guibaudo showed that if a parasitic series resistance were negligible and BDS is small, the Y function is ID divided by the square root of the transconductance. The Y function will not depend on the mobility degradation. So this was proved by Guibaudo in 1988. So then by plotting the Y function as a function of BGS, you will get from the intersect the threshold voltage, and from the slope you get K. On the other hand, the same year, Jain demonstrated that if the mobility degradation were negligible and BDS is small, the Y function will be independent of parasitic series resistance. So he assumed this, he solved this, and he showed that Y is equal to this. So the same function for different application and different publication. 1994, 1996, the asymmetric series resistance extraction method for MOSFET, for 4-terminal MOSFET. The first two methods are the constant current extrapolation method, and the second is the transconductance method. And they are assuming this model, and it's a 4-terminal device. Year 2001, the H method for non-crystalline MOSFET. The first one, year 2001, the function H1. Function H1, if you assume that for weak inversion, the current is like this, and function H1 is the integration of I with respect to Vg divided by I, you get that the function of this function H1, after you do the mathematics, is equal to MVTH. So that means that the weak inversion conduction will allow you to extract the parameter N, which is the subthreshold slope, which is related to the subthreshold slope. For a strong inversion, the current is modeled like this. If you do the mathematics, function H1 will yield to a straight line. So from the straight line, you get the threshold voltage, and from the slope, you get parameter M. The use of H1 is an improvement over the derivative method regarding data noise reduction. However, because H1 still contains a current in the denominator, the effect of the noise can be further reduced. And then a function H2 was proposed. Function H2 is defined here. If you do the mathematics for weak inversion, you get is equal M VTH, which allows to extract M from a constant value. For strong inversion, if you do this model and you substitute for the function, you will get a straight line, which allows you to extract M and VTH from the straight line. The use of H2 is an improvement with respect to H1 regarding data noise reduction. And here we have both procedures for a polysilicon nanowire MOSFET. And here we have the transfer characteristic. Here we have the output characteristic. Here we have H1 and H2. We see H1 is a lot noisy. It has more noise than function H2. And here we have the extraction. Transconductance to current ratio. This was done in year 2010. The idea is that the function is defined like the transconductance divided by ID. If you this can be rewritten like this, and basically this is related to the S, where S is the subthreshold slope factor. This method can be related to a previous publication from 1995 by Aoyama. Aoyama who proposed that VT can be determined as the gate voltage at which the second derivative of the logarithmic of the drain current take a minimum value. The second derivative of the logarithmic of the drain current with respect to VG is the derivative of TCR with respect to VG. Year 2050, the gate-all-around MOSFET inspired the nanowire device. This is the gate-all-around MOSFET. This is the nanowire. The nanowire is this one transistor here, one transistor here, and one transistor here, but they are parallel and one on top of the other. Year 2050, the thin film and the nanowire spine the nanochip. There is a nanowire. The nanochip looks like the difference is that it is wider. So this is the nanochip. The back-enhanced SOI MOSFET, they present a simple fabrication process without any doping and with only 3 lithography steps. The operation principle of the SOI MOSFET, of this BE SOI MOSFET is given here. So then the idea is you don't have any lithography, any doping, and the idea is the gate deplete or enhance the conduction. It is interesting that this device has a effect on the contact here. So the effect in the contact here is modeled by 2 anti-parallel diodes. Year 2006, a method based on constant current and a plot of EDS as a function of VGS is presented. And here are the details, and here is an approximated equation for R that can be used also. Year 2007, recent innovation that have been used. Among them, we find strain silicon, year 2003, high K metal, year 2007, and year 2011, the FinFET. Year 2020, the asymmetric series resistance extraction method for 3-terminal MOSFET. The idea is now you have a thin film transistor that has no body contact, so you have this. So the method to extract the difference in the resistance are 3: improved constant current extrapolation method, the H function method, and the alternated current-based method, which was just recently presented in Electron Device Letter. Conclusion: parameter extraction method for diodes, solar cell, and MOSFET has been reviewed. The methods are presented in chronological order, and they are separated in 2 groups: diode, solar cell, and MOSFET. The use of integration-based mathematical procedure is a powerful tool for parameter extraction, and then the integration reduces measurement noise. Fin da presentación. Obrigado pela sua atenção. Es una honra, un placer visitar virtualmente o Brasil. Eu realmente agradezco este convite. Será um prazer enviar-lhe uma cópia da minha apresentação se você solicita por e-mail. Mi e-mail ortiz@iee.org. Okay.
Thank you very much, Adelmo. It was very good, an excellent talk. Okay, a very good overview of many methods. I think many of the peoples know some of the method, but not everyone. That's a good idea to see what's the difference between them. And I think it's very useful for everyone. Thank you very much, Adelmo.
You're more welcome. Shall I stop sharing or shall I stay with the presentation?
Yes, because then you can see the chat. Please look at the chat and I'll send you the question, right?
Okay.
Okay. The first question from the audience here, please. What is the main function to extract the threshold voltage nowadays? Is for IDS model or reliability?
That's a very good question. And that also teaches us that anything that you learn, the knowledge is valid for a period of time. The reason is the following. At the very beginning, in the 60s, 70s, the threshold voltage was very important for circuit simulation because SPICE level 1 used threshold voltage. But then in the 80s and in the 90s, the threshold voltage is not important anymore for circuit simulation. They have a more, for example, the power and sum model is not based on threshold voltage. The power sum model is the basis of all advanced MOSFET model. And they are the advanced MOSFET model are based on surface potential, not threshold voltage. But on the other hand, you may think, oh, the threshold voltage is not important anymore. No, the threshold voltage is very important for reliability because when they fabricate devices, they want to know how good the device and how long the device will last. And the threshold voltage is fundamental. So nowadays, reliability is important of threshold voltage.
Thank you for the answer. Now there is another question from the YouTube. Paula put in your chat. Which model do you think is the most suitable to estimate the series resistance for nano?
Nano wire. Well, that's also a good question. Of course, my opinion is biased, and my opinion is biased because since I have developed some of the model, I try to use my model. So I think, for example, the constant ID is a method that can be tried. That's a very recent method that was developed by Roberto Murphy and Rey Denzel Torres and us. That method is interesting. Or the other method that can be also used is the integration method. The integration methods are also can be tried.
Perhaps you could show for us the slides of this method to be easier for the people to understand.
Okay, let me see. Present now.
Yes.
Your entire screen. Here, okay. This paper, the first author is Andrea Sucre, and the other author are not here because we have no space, but they are from Mexico and from Venezuela.
Right.
And in this paper, the idea is you can solve BDS as a function of this, and then the idea is this equation can be used for fitting, because BDS is relatively simple equation as a function of ID. But you can also use an approximated equation, which is this one. So that means if you measure, if you have a measure of 2 current and 2 drain voltage, you can extract R like this. And the other method that I was thinking about integration is this one, H1 and H2. Here H2, the idea is to measure the current as a function of gate voltage and integrate. Either here is the function H1 is simple, and the idea if you measure the current, well, for a strong inversion it will be something like if you have a current like this, you have this. So this is what I was thinking, but of course maybe I will need maybe in order to answer the question better, I will need more time to think. Maybe I can write to you later.
Thank you for your answer. Another question from Walter Salcedo. It's in the chat. Within the scenario of different methods, they can certainly give different values of the parameters. Which model can be more reliable?
Which model can be? Well, that's a very good question. Definitely is a very good question, and there is no good answer for it. Because, for example, in the case of the diode, we use the same model, and we use different parameter extraction, and we extract different parameters. So, what is the best method to extract the parameter? Well, for example, Norde was very good if your solution is very close to the point where the minimum is. On the other hand, if you do fitting, the fitting will minimize the errors. So then, depending how do you define the best model? There is no general answer. Okay. Now that there are many available methods for parameter extraction, are there good books that compile this information? So would you recommend one? Well, a good book for parameter extraction.
Your book.
Well, of course, that's another unbiased opinion. But yes, but I guess so far I don't know. I guess there are papers, but no, I don't know good book. No.
But that paper that you compare all the methods, I think is a very good one, right?
Yes. For the threshold voltage, there are two papers that we published. The first paper was year 2002.
Right.
And the paper, we wrote the paper and again, this is another example that you never know what you are doing. That paper was motivated because the editor invited us to write a paper, an invited paper. So we decided, let's do a paper about threshold voltage because we have learned a little bit about it. And so, at the time, I was thinking, well, that was a paper. I don't know how good it's going to be. And the result is, that is the paper that I have had more citations. I don't know how many citations has, but I think it's more than 200. And I was not expecting that. And the paper was so good that 10 years later, we did a renewal of the paper. We do an updated paper.
And only for the information for the audience, the name of your paper, the year, and the periodic is IEEE LED device ladder. In that case, no. That paper where you compare all the threshold voltage method.
No, microelectronics and reliability.
Microelectronic reliability, which year for the audience?
The first year is year 2002. Right. And then we did an updated version of the paper in year 2013, I think.
Okay, great. I think it's good for the people who is interested in these topics, right? Good. Okay, I think it's okay for us. It's enough. Now it's 10 past noon. I think it's enough for everyone. Thank you very much for the excellent talk.